Hello everybody. First of all and before we begin, I want to thank the Nano Conference community for presenting this work. My name is Mohamed TIHTIH from Morocco. I'm a PhD student at the Faculty of Science Dar al Laboratory of Theoretical and Applied Physics. In this work, I'm going to show to you my work entitled under First Principles Calculations of the Structural and Electronic Properties of Barium and Light Titanate. First, I'd like to tell you about why I'm interested in this work. Then I will be showing you the aspects of first principles calculations used in this simulation. After that, I will move the method of simulations. Then I will be looking to our results and discussion, and I will finish it with a conclusion and perspectives. So as introduction, BaTiO3 perovskite oxides such as lead and barium titanate are an important family of multifunctional compounds due to their high dielectric and piezoelectric responses. These materials are attractive for numerous technological applications such as electronics, catalysis, superconductors, and electromechanical energy conversion. Recently, major efforts have been investigated in designing new lead-free piezoelectric oxides in order to minimize environmental damage. First principles methods based on density functional theory have been widely used to explore the ferroelectric phase transitions metal oxide at the atomistic level. In this work, we are using the density functional theory to study the structural and electronic properties of perovskites such as barium and light titanate tape using the generalized gradient approximation. We show the tetragonal structures of barium and light titanate used in our simulations, and it is plotted using Vista package, where Pb and Be two place ions are in these corners. They have a tetragonal structure symmetry. The O2 less ions are displaced below the centers of each of the 6 phases, and the Te4 place ion is displaced upward from the unit cell center by the same amount. Some applications of our materials, barium and light titanate, are perovskite materials that are used by the electronics industry as a base material in the manufacture of multi-rod capacitors, layer capacitors, thermistors, gas and moisture sensors. These perovskites are also very promising and find more and more applications in transparent ceramics, no-pollutant dyes, photovoltaic cells, or fuel cells. Now I'm going to talk about theoretical aspects of our first principle calculations. Main difficulty in solving the Schrödinger equation for a real material is that the potential energy of the system depends on the positions of all the electronics and nuclei, and in general is not separable. In order to make these equations tractable, approximations have to be made. The first such approximation is the Born-Oppenheimer approximation. This is based on the observation that the mass of an electron is roughly 2000 times smaller than the mass of a proton, leading to the conclusion that the electrons can be considered to respond instantaneously to any change in the positions of nuclei. As a result, for fixed configuration of the nuclei, the electrons may be considered to be governed by a Schrödinger equation where the nuclei are in static arrangement, and the nuclei to be governed by a Schrödinger equation in which the effective potential contained the energy associated the equilibrium electronic configuration. The purpose of the DFT is to determine the physical property of the ground state of an interaction multi-electron system. It is based on a fundamental theorem that is divided in 2 parts, demonstrated by Hohenberg and Cohen, where the Cohen-Sham theory is based on the hypothesis that it is possible to reproduce the ground state density of a system of interaction particles by an auxiliary system consisting of independent particles. The real system consisting of interaction electron is replaced by a set of friction and independent particles evolving in a effective potential. Although n-body interaction begin contained in an electron density dependent exchange and correlation function given by the Hamiltonian mentioned below. To translate these theoretical aspects, we choose quantum espresso as numerical simulation code. All the FT calculations in our work were performed using the PlanWave-based quantum espresso software package. The energy cutoff for the PlanWave-based state was 50 and 200 for the charge density cutoff, along with ultra-soft pseudo-potentials that represents the electron-ion interaction. This cutoff criterion has also been employed in height to fit the FT calculations using the ultra-soft pseudo-potential library as shown in Table 2. As for the valence orbitals, we have worked with the valence orbitals mentioned in Table 1, and a k-point match of 444 was determined to be sufficient for sampling the Brillouin zone. So to validate our calculation, we will compare the result obtained with the experiment's results. Results calculated for barium and light titanate are in agreement with previously published experiment results. The calculated relaxed lattice parameters given a ratio 1.03 for barium titanate and a given a ratio of 1.11 for light titanate, and we find that the materials preserve the tetragonal structure. As you can see in Table 3, optimized network parameters are presented and compared with previously published experimental work. They have highly constrained networks due to strong orbital hybridization and significant no-center symmetric distortion of the network. Barium and light titanate have the highest tetragonal distortion, making it significantly more ferroelectric. Related network parameters underestimate the band gap and overestimate previously published data. The generalized gradient approximation function confirmed the capacity of barium and light titanate for solid-state applications, as shown in Table 4. The result of the band gap by generalized gradient approximation lay within the visible range of this material. The band structural diagram for barium and light titanate is shown in Figure 2. The conduction bands are displaced upward and the valence band down to the well-known underestimate of the generalized gradient approximation from band energy. Figure 2 shows the total state density of tetragonal barium and light titanate using the generalized gradient approximations as a function of energy ranging from less 50 electron volt to 20 electron volt. The highest density of state peak in the valence band was about less 35 electron volts because the peak distribution appears much more clearly in the valence band than in the conduction band. The band gap of tetragonal barium titanate is about 1.69 electron volts for barium titanate and 2.09 for light titanate because it is the region of energy that separates the valence and conduction bands that does not contain any electronic state. This work, the optimized match parameters and the index band gap are calculated using quantum espresso. We find that barium and light titanate preserve the tetragonal structure. Our results show that the quantum espresso code has effective capability for finding network parameters and adjusting the band gap in perovskite structures. As perspectives, study of barium and light titanate materials with local density approximation, study of the doping effect on perovskite barium and light titanate compounds, and first principle study of the mobility of barium and light titanate. Thank you for your attention.